Base64 encoding, we use it every single day. So much that you use it, it's almost every minute. It's in use, and on your phone, on your laptop, you are using Base64 encoding. As a software engineer, you might not always use Base64 encoding from a development perspective as you're writing code. However, you are using Base64 encoding as a user of a system, and many systems use this. The biggest user, I didn't know this a while ago, but the biggest user of Base64 encoding is anything to do with emails and email attachments. Yes, isn't it weird? All those email attachments, as they come over through your inbox, guess what? They're not binary encoded, they're Base64 encoded. And there's a general problem with that, but there's also a benefit. Let's first talk about the benefit of Base64 encoding within an email system. For example, as you're sending a message over an email system, it's all in ASCII, right? All that text, it's all text essentially. And so what you have the opportunity to do is maybe add some more text to it, but it could be in the form of an attachment. Yes, that's right. So you can set a boundary of where you're about to say, hey, this is the following information is going to be represented as text, but it's actually an image represented in ASCII format. This happens every day, constantly, and you're using it as a regular basis. But it goes beyond just email. You use Base64 encoding in a lot of other places. The other, I would say the second most common use case for Base64 encoding is in regards to secure authentication. When you sign into a website, you are granted sort of a token or an ID that's usually based on a TTL, or it's a session ID, right? And this is based off of a secure hash of information that you provided as credentials to the provider. And in this case, like an email or password can then be provided as a hash when it's stored in the database. So that way it doesn't need to be stored in plain text, right? Providers should not store your credentials in their original form. It should be secured and abstracted in a way that can be then later verified if you supply the correct information. When providers store your credential, they usually use an algorithm that's secure, like SHA-256, that takes a hash of your credentials and stores that into a database. And usually when we store that data into a database, that is represented as Base64, so we can store it as ASCII, which is text, which is perfectly fine. And when you would have to store it as binary otherwise, which has some implications because of how the bits are used and leveraged. So it's better from a database perspective to fill in the bits in a uniform fashion using Base64 encoding. JSON Web Tokens also include a SHA-256 or another crypto algorithm that is represented in a Base64 encoded format. We don't want to pass over that data. Since it's usually in an HTTP header, that data needs to be in ASCII format, so it must be encoded using Base64 encoding. Some other common use cases are images within CSS, like SVG, PNG, JPEG. Those can be encoded from their binary format into, yes right, Base64 encoded. And you might be thinking, oh, wait a second, for the SVG, that's already in text format. Well, they also include interesting characters that are usually brackets, which is mentioned in here. These are generally less safe characters, and when you Base64 encode it, it turns it into safe characters that look a lot more like this. And they're more transportable and also more friendly into the various formats that they might be represented in. So now we have a pretty good picture of why we like to use Base64 encoding, turning that binary data into an ASCII format that can be represented in the ASCII environment or Unicode environment or UTF-8 environment, right? All those things would be compatible in this case. And there's a drawback. Let's talk about the drawback really quick. It's less efficient because it takes up more bits. And then that sounds terrible, right? Because if you have a very big file that you're trying to convert into Base64, you're going to be inflating it by about 33%. Base64 encoding has a lot of use cases taking that binary data into the ASCII world, which is fantastic. We love it. There is a drawback, however, that 33% is increased in bit consumption. That's because it essentially is, for the most part, what I'm reading and what I understand here, it's thrown away. We only need 6 bits of the 8-bit octet, right? Because in computer world, we think in terms of bytes, right? every 8-bit is 1 byte. And that means that as we convert our data from binary into ASCII, we have a little bit of wastage. So let's take an example use case here. We have 8 bits represented with some ASCII characters. The author's name is being used as an example. Actually, we see that there's 1, 2, 3, 4, 5, 6 different letters here represented in standard ASCII format, right, which requires octets. But in Base64 encoding, we translate that into 6 bits, which requires us to expand this out from 6 bytes into extra chunks here. So we see that there's 2 extra portions that then need to be divided into 1, 2, 3, 4, 5, 6, 7, 8 instead of the 6. So that means that there's 2 extra representations here that are being added into the system that is required in order to format that into a Base64 encoding. And herein lies the wastage that we see, that 30% overhead. As we can see here, the author explains converting their name into Base64, and you can see it's a little bit, there's a few extra characters. And what is the point here in this case? Well, the example is mostly converting ASCII to ASCII. We don't need to do that in the real world. This is just a for instance. But in this case, it gives you a really good idea of what converting that binary data into ASCII data kind of looks like from the overhead that we see, right? That's important to represent here, because you need to know what that trade-off is. If you're having a very big file, it might be best for you to leave it in binary format and just include a reference link of some sort rather than embedding it into somewhere using Base64. Just to show you a quick example of what that looks like here, we've got the author's name, then we can say B2A in our Chrome or any web browser here, and you can see it converts that into Base64 encoding, which matches here. We can also convert it backwards to, it's commutative, right? So we can go both ways, A to B, and this returns it back to the original name. Let's walk through how that works step by step. Base64 encoding algorithm is fairly straightforward. As you can see here, there's 4 steps. The first step is only required if you're starting with text, because usually with Base64 encoding you're starting with binary, and that's where you start. So you really only need the last 3 steps there. The first step is necessary if you're starting with text. So you convert that into its binary representation, which in this case, would be ASCII, which is those 8 bits, the octets that represent each character. And then after you've done that, now you convert and divide all those bits of 8 bits into its 6-bit counterparts, which means that you're going to end up with more groups, because you would start with 8, right? 8 bits. If you slice that down by 6, then you're immediately going to have 2 segments, and those need to get expanded out into the ASCII space, again into the 8-bit space. See, in the worst case scenario, when you're encoding 1 byte, you will end up with 2 bytes consumed. So that's the worst case. Usually you're going to have more. So we don't have to worry about that in that case. But let's walk through this. So we take the text, we convert it to binary. It's that 8 bits per text, so characters. Then we take those, divide them into groups of 6, and then we convert each of those into the decimal number for the 0 to 63, which represents our ability to use a lookup table for the Base64 alphabet. And the Base64 alphabet is represented by A to Z, 0 to 9, and the capital of A to Z, right? So that's 26 times 2 and then plus 10, but that doesn't get us all the way there. So we need to add a couple of extra characters, and those usually are through some extra offerings through the paddings. I believe there's also a / in there. Calculating this really quick, we can say 26 plus 26 for the uppercase and lowercase versions of the alphabet. And then we also have 0 to 9, which is 10. So we can say plus 10. But that leaves 2 extra characters in there. One would be the equal sign, and another is the /, I believe. All right, walking through the example here, caches, we've got 1, 2, 3, 4, 5, 6 bytes. These are the octets represented in ASCII. We convert those into groups of 6, right? So then that means that we're going to have 2 extras, because we converted those chunks, like say, scrush all these bits together, and then we're going to start slicing them into groups of 6, which ends up looking like this. Then we jump down here, and then we convert those into the Base64 integer values, which will then be used in the lookup table, which is a fairly simple algorithm, to convert those back into ASCII space. So we see that's how it's done. It's pretty straightforward. The one downside that I'm a little bit disappointed in is that we have to throw away a few bits. And but why? Why do we have to throw away those bits? There is a reason. I'm not necessarily super satisfied with the reason, but there is a reason. That 33% comes at a loss with throwing away those initial bits here in the world of computers. We love things in powers of 2. That's because we're in a binary system and the system runs in binary. We also generally chunk things in an octet, right? So that's 8. With Base64, we divide things into 6 bits. So we're kind of tossing away those 2 bits there for every byte, and therein lies where it's less efficient, right? We expand the data volume size because we're always because as we're reinflating it into ASCII, we have to represent. ASCII is in 8 bits, right? And so, but Base64 turns it into 6 bits, back into 8 bits. Therein lies the wastage, and there is that good reason of this is specifically because of how we transmit our octets over the internet. And say, for example, we were to pack in everything. We use every single bit, which is what I want. I would love us to just use every single bit the way much as possibly as we can. For Base64 encoding, since it's converted into ASCII, there's not really a good way to pack those bits. We would need to, it wouldn't be Base64 anymore. It would be, Base256. Then we could fully consume those octets, and we could also represent it in terms of ASCII at that point, and it would be legitimate. But there's a problem with doing that, and that specific problem is now we have to expand our ASCII to 100% of that base, which includes non-printable characters, return characters, unsafe symbols that don't really work well in many of the environments that we leverage in Base64, such as HTML or CSS or emails or JSON web tokens. Those things have delimiters that they depend on, and if we went all the way and consumed every single bit, we would not be able to leverage exactly what we're looking for from those bits. We have to throw those 2 bits away. We just have to. So we have to waste those bits. And we've been doing it for decades. Just imagine how much data has been thrown away from all of this. But that's what Base64 is. It allows us to take that binary and represent it in an ASCII environment, which is the majority of the internet's communication, and do it in a way that's safe for that ASCII environment without having to use special characters or delimiters that each of these environments depend upon. Base64 encoding is so universal that it's included in every language. And we can see here, for example, that this is the Ruby on Rails, or just Ruby in general. We don't need to call it Ruby. This is Ruby's Base64 library. All you have to do is import it and then leverage it like this. It's so simple, because we use it on a regular basis with those web tokens and you name it. This is C#. Love C#. It's a great language, and you can see here's an example of converting and decoding. Here's another example, PHP. They've got global functions that are just defined as a matter of fact because they are used that frequently. Same with JavaScript. We've got those globals, and they are very interestingly, they're cryptic. I would say they're cryptic. What is that function? What is it? Binary to ASCII. That's very simple. I mean, it could be Base64 to ASCII, but that does not make sense. I would say that's a binary to ASCII. That's what the B and the A stand for. And then in your terminal window, we can see here that there's a universally installed Base64 command that does this in your terminal window. Thank you to Akshay, who wrote this blog post around Base64 encoding. Guess what? It's so important because we use it every day, every second. And now you know a little bit more about how Base64 encoding works and how you can leverage it. Also, the pitfalls with the extra size and its wastefulness with those 2 bits that it likes to throw away. So I'm not going to use those bits, but it's for a good reason that we found out earlier. And guess what? It's something that has been used for decades. It is still in use today, and we don't really have any plans to make anything better. We're essentially staying with Base64, and it's the way to go going forward.